We'll begin our momentum and impulse homework here with this conceptual question where we have to explain the following scenarios using what we know about impulse. So the first one is airbags keep you protected in a car during a collision, and the key word here is time. Okay, what airbags do is they extend the time of the collision, which decreases the force, and it really all goes back to our equation that we have for impulse. The impulse is equal to the average force multiplied by the change in time. So we can see that for a given collision, for a given delta p, force and time are inversely proportional. So increasing the time decreases the force and keeps you safe. For part B, we're asked to consider this scenario up here where a golf ball is compressed while a golf club is hitting it. And we want to talk about why that compression helps to increase the distance that the ball travels. And once again, the key concept here is time, but we're going to apply it in a slightly different way. So we're still thinking about delta P equals our average force multiplied by our change in time. However, in this situation, we'll assume that we have a constant average force exerted on the ball by the golf club. So if our force is constant, what ends up happening is increasing the time will ultimately increase the impulse and therefore increase the velocity of the ball and increase the distance that it travels. So we have a situation here where we have two boxes with the same force applied to them. We'll call that F. While they're on a frictionless surface, we do know that box A is going to have more mass here than box B. So the first question we're asked is which one experiences a greater impulse during this time, and the answer is they experience the same impulse. All right, we can think about our equation, delta P equals our average force multiplied by the change in time. So if they have the same force and that force is exerted for the same amount of time, that means that our impulse is the same. For B, we want to know which one has a greater velocity after time t, and that's going to be box B. We know from part A that they have the same impulse, and we also know that impulse is equal to mass times the change in velocity. So since box B has the smaller mass out of the two, it must have a greater change in velocity, and therefore is traveling faster after this period of time t. Whereas box A is more mass, so it's going to have a smaller change in velocity. And the last question here asks us which box has more work done on it, and that is also going to be box B. There's two ways of explaining it. We could think, first of all, about kinetic energy, and we could say that kinetic energy is 1/2 mv squared, and we could say that box A has more mass, box B has more velocity, but because of the fact that it is proportional to v squared, that increase in velocity affects it more so, and therefore box B ends with more energy and therefore had more work done on it. The other way we could explain it is by thinking about our other way of finding work, which is F delta x cosine theta. Now they both had the same force acting on them, but because box B had less mass, its displacement is going to be bigger, and that greater displacement means that more work is going to be done on box B, since the same force will move it a further distance in a given time. Moving on to our next question here, we have a bowling ball that's traveling at a speed of v when it has a head-on collision with two pins. And we see here the graph of the force versus time for its collision with pin 1 and its collision with pin 2. And so the first thing we want to figure out is what is the magnitude of the change in momentum of the ball, and that's just going to be the area under the curve here, which represents the impulse or the change in the momentum. So I'm going to find the area for each one of those. So we're going to have area 1, which is going to be that rectangle there, base times height, so it's just going to be F times t. And I'm going to have area 2, which is going to be this triangle here, and that's going to be 1/2 base times height. So it's going to be 1/2 ft, and when we combine those, we end up getting a total area here of 3/2 ft. For B, we want to know what is the magnitude of the total impulse delivered to the two pins combined, and that's going to be the same as the bowling ball. We know they exert equal forces on each other, so that means that the change in momentum for the two pins is going to be the same as the bowling ball. So 3/2 ft. For part C here, we're told that after colliding with the first pin, it's traveling at 9/10 v, which is 9/10 of its initial speed. And so that's at this point right here after colliding with the first pin, and we want to know how fast it's traveling at point 3t after it's also collided with the second bowling pin. So we're going to go ahead and we could reason our way through this. Okay, we see that the impulse for the first pin was ft, and the impulse for the second one was 1/2 ft. So that means that our change in velocity for the second pin is going to be 1/2 of the change in velocity of the first, which was 1/10 v. So it's really a change of 1/20th v. And so if we want, we can just subtract that change from our velocity after colliding with the first pin, so 9/10 v, minus the amount we lose after colliding with the second pin, 1/20th v. And what we can do then is find a common denominator, so 9/10 v is really 18/20 v. And then when we subtract them, we get a new velocity here of 17/20 v. So that's one way of doing it. We also, if we would like, can do it a little bit more formally. So after the first pin, we can say our change in momentum was ft, and what that led to was a change in the velocity. So we also know that change in momentum is mass times change in velocity. So we can say that ft is equal to mass times our change in velocity, 9/10 v minus v, or negative 1/10 v. Once we have that for the first collision, we can think about our second collision. And so for the second collision, our change in momentum was 1/2 ft. And once again, we can set that equal to mass times change in velocity here. And we're going to do two things. Number one, we're going to plug in this expression that we have for ft. And we're also going to plug in what we know about our change in velocity. So we can say 1/2 times m times negative 1/10 v, that expression for ft, and that's going to be equal to our mass times our change in velocity, v final minus v initial, so v final, that's what we're solving for, minus 9/10 v, which was the velocity when it first collided with this pin. And so we can go ahead and cancel out our m's here, and what we end up getting is negative 1/20th v equals v final minus 9/10 v, and we add that 9/10 v over to the other side, combine those fractions, and we end up getting an answer once again of 17/20 v. So for the next part, we want to figure out the speed of each pin after the collision. So I'm going to start with conservation momentum, pi equals pf, and I'm going to think about this collision here between the bowling ball, which I'll call object 1, traveling at a speed of v, and the pin, which I'll call object 2, that was initially at rest. And we want to figure out the velocity of the pin afterwards. So I'm going to say initially we have m1, v1, just the bowling ball has momentum initially, and after the collision, both the bowling ball, m1, v1f, and the pin, m2, v2f, have momentum. Now we know a few things about the mass. We know that the bowling ball has 10 times as much mass, so I'm going to call it 10m, and its velocity initially is v, and that's going to be equal to 10m times 9/10 v, plus the mass of the bowling ball, which is just m, times vf. I can go ahead and cancel out the m's in every single term here, and what I'm left with is 10v equals 9v plus vf, which means that the final velocity for pin 1 is just going to be v, which happened to be the initial velocity of the bowling ball. For the last one, I'm going to set up conservation of momentum once again, but now I'm going to be thinking about the bowling ball colliding with, we'll call it object 3 here, the second pin, and now the bowling ball is only moving at a speed of 9/10 v. And so we set up our conservation momentum once again, so m1 v1 initial equals m1 v1 final, plus, and I'll call it just m3 v3 final. And that's the velocity we're ultimately looking for. So once again, it's going to be 10m times 9/10 v equals 10m times 17/20 v plus m times that v final that we're looking for object 3, which is the second bowling pin. We cancel out the m's, do a little math to simplify here, and so we have 9v is going to be equal to 8.5 v if we just do it as a decimal, plus vf. So our final velocity here ends up being 0.5 v, or 1/2 v. For this next one here, we're told about a roller coaster that launches riders from rest to a speed of v over some period of time. And we have the graph of the force exerted on the passengers as a function of time. And we're also told that the maximum force cannot exceed 2.5 times the person's weight, so 2.5 times Fg. And what we want to do is derive an expression for the minimum amount of time for the acceleration of the roller coaster that will keep riders safe. So I'm going to start out by finding my change of momentum, my impulse. And what I'm going to use first is m delta v. So we're going to have riders with some mass m. We're not actually told that, but I'll worry about that later. And we know that we're accelerating them from rest to a speed of v, which means my change in velocity is going to be v, that final velocity, minus 0, my initial velocity. So my impulse, my change in momentum, is just going to be mv, where v is this velocity that the riders reach. The other thing that I'm going to do is I'm going to use this graph sum. So if I think about the area under the curve on this graph, okay, thinking about the area of that triangle, the impulse is also going to be equal to 1/2 base times height. And so I end up getting an impulse using the graph of 1/2 f max times this time here, t. Now, I'm told that F max is equal to 2.5 times my weight, or 2.5 times the rider's weight. So I'm going to substitute in 2.5 mg, right? Because weight is the force of gravity. And so there I have that expression. And so what I can ultimately do is bring these two expressions together and solve for time. So I can say mv equals 1/2 times 2.5 mg times my time. The mass cancels out here, and now it doesn't matter what my mass was. And I'm going to multiply both sides by 2 and divide by 2.5g, so I get 2v, getting rid of the 1/2, over 2.5g equals my time. And I can go ahead and simplify that. That ends up becoming just 4/5 v over g. For this next one, we have a situation where we have a tennis ball and a piece of clay both being thrown at a hanging block here. They're thrown with the same mass, they're thrown with the same speed, but the tennis ball hits the block and rebounds, whereas the clay hits the block and sticks to it. And we want to know which situation will result in the block swinging up to a greater height. And so the answer here is going to end up being the tennis ball. And there's a few ways to explain it, but I think the easiest way is to realize that the tennis ball is initially traveling to the right, and then when it rebounds, its velocity is back to the left, whereas the clay continues moving to the right. It obviously sticks to the box, but the clay is still moving to the right. So the tennis ball has a greater change in momentum, okay? And we know that the change in momentum of these two objects when they collide is going to be the same. All right, so since the tennis ball undergoes a greater change in momentum bouncing off of the block, that means the block gains more momentum and therefore swings up to a greater height because it's traveling faster. So for this problem, we have basically a recoil situation. We have a person standing at rest holding a medicine ball. They then throw the medicine ball in one direction at some speed v, and that's going to cause the person to move in the opposite direction at some speed that we are looking for. Now we know that the mass of the person is 20 times the mass of the ball, so I'll say the person's mass is 20 m, and the mass of the ball is just m. I'm going to go ahead then and set up momentum initial equals momentum final to conserve momentum. So initially there is no momentum in my system, neither object is moving. However, after they explode apart, we have both objects moving separately. Okay, we'll call the person 1 and the medicine ball 2. So this gives me 0 equals 20 m times the velocity of the person, which I'll just leave as v1, plus m, the mass of the ball, times v, the velocity of the ball. So we can go ahead and solve. The masses cancel out here because it's in every term, and we end up getting that the velocity of the person afterwards is just going to be v over 20. Now, depending on how you set this up, you could have gotten a negative sign in here for your final velocity. The way I set it up actually does result in a negative sign there, but I'm not going to include that negative sign for two reasons. Number one, it really just says how fast will he be moving. Okay, so that's really asking about the speed, which is just the magnitude of the velocity. And also, the other reason is depending on how I set it up, I could have gotten a positive. If I had said that the ball was thrown in the negative direction, that would result in a positive velocity for Brian. So I'm just going to leave it as v over 20, but certainly on a test, either one would be acceptable, but probably the question would ask for the magnitude of the velocity. Second question asks about the velocity of the center of mass of the system after the ball is thrown, and that's going to remain 0, and this one we don't have to do math with, but we can explain. So we know that initially the velocity of the center of mass of the system is 0 because both objects are at rest. Since we have no outside forces acting on our system here, we can assume, or we can say that the final velocity of the center of mass is going to be 0 because there are no outside forces. So even though each object is moving, they're moving in opposite directions, and the velocity of the center of mass of the system is just 0. For this next one, we have a child running and then jumping on a stationary shopping cart. We know the child is initially running at a speed of v, and the shopping cart is at rest. Afterwards, the child is on the shopping cart, and we know that that system is traveling at a speed of 9/10 v. So we first want to determine what is the mass of the shopping cart. So I'm going to go ahead and set up conservation of momentum. I'll say that the child is object 1, the cart is object 2. So before the collision, we just have object 1 that has momentum. After the collision, they're moving together, so we're going to combine their masses. So I'm going to say m1 plus m2 times the final velocity of the system. So the child, we're told, is a mass of m, so I'm going to plug that in as m. We know this initial velocity is v, and that's going to be equal to m plus m2, the mass of the cart, times 9/10 v. So what we can go ahead and do is distribute that 9/10 v to both of those terms. So we get mv equals 9/10 mv plus m2 times 9/10 v. We subtract that 9/10 mv from both sides, and so we have 1/10 mv equals 9/10 m2v. We can cancel out a few things here. The v's go away, the 10s can go away. And so what we're left with is that the shopping cart has a mass of m over 9, 1/9 the mass of the child. That was for part A. For part B here, we want to know the average force exerted on the child. So I'm going to start by finding the impulse of the child, the change in momentum. So that's going to be the mass of the child, which is just m, times delta v. So it's going to be 9/10 v was the final velocity, minus v was the initial velocity. And so I get that the impulse is going to be negative 1/10 mv. I'm going to go ahead and simplify that. And I can use that to get the average force. I know that the impulse is also equal to the average force times my change in time. So I can say negative 1/10 mv is equal to the average force multiplied by this time t here that we have for the length of the collision. And so when I go ahead and solve that, I get that the average force is negative mv over 10t. We're usually just going to solve for the magnitude though, so I'm just going to put it in as mv over 10t. And that really goes back to the idea that we could have picked either direction to be the positive direction, and that would have given us a different answer. So the magnitude of the force is mv over 10t. Depending on what sign you picked, you could get a negative for that answer. For part C, we could go through and do the math here to find the average force on the shopping cart, but I know my concepts, and due to Newton's third law, I know that those forces are equal and opposite, so the force on the shopping cart is also going to be mv over 10t. Moving on to this next one, we have a child, Kyle, running and jumping onto a sled. And so Kyle's initially running at some speed here, v. He runs and jumps on the sled, so now Kyle and the sled are moving together at some new speed. And then they're going to go ahead and descend this hill that has a height of h. And what we're ultimately looking for is the velocity here when they get to the bottom of the hill. So the first thing I'm going to do here is I'm going to focus on this collision, and I'm going to do that by setting up my conservation of momentum. And so initially we just have Kyle moving, Alright, so it's just going to be m1, v1. Afterwards, Kyle and the sled are moving together, so m1 plus m2 times v final. Their combined velocity. And so I can plug in the things I know. I know this mass is just m times the other mass, or times the velocity, which is v. And that's going to be equal to m plus m over 4 times v final. And so I end up getting mv equals m plus m over 4 is really 5/4 m times v final. And so if we go ahead and cancel out the m's there, I find that my final velocity here is just going to be 4/5 v. So 4/5 of that initial velocity. I'm now going to think about this transition down the hill. During that time, momentum is not conserved because we have that outside force of gravity acting on our system. However, energy is conserved, and so I can go ahead and set up my conservation of energy for that scenario. So I have initially gravitational potential energy plus kinetic energy, okay? And then at the end of the hill, I'm left with just kinetic energy, the final kinetic and the initial kinetic. So I can say mgh plus 1/2 mv squared is going to be equal to 1/2 mv final squared, and that's that velocity I'm ultimately looking for. I see the masses here will just cancel out. And so what I end up getting is gh plus 1/2 times 4/5 v, that quantity squared, equals 1/2 times v final squared. I'm going to deal with this 4/5 v. I'm going to go ahead and square that, and I'm going to multiply both sides by 2 to get rid of the 1/2. And what I end up getting is 2gh plus 4/5 squared gives me 16/25 v squared, and the 1/2 and the 2 cancel out. And then the square root of that is going to be equal to vf. So there's my final answer. The square root of 2gh plus 16/25 v squared, where that v is the initial velocity of Kyle right here. We then have two conceptual questions. First, does the velocity of the center of mass of the system change during the collision? And the answer to that is no. And the reason is there are no outside forces acting on the system, so the velocity of the center of mass remains the same. Second question asks if the velocity of the center of mass changes as we go down the hill. And in that case, it does change because there's a force of gravity acting on the object as we descend the hill. That is an outside force, and that changes the velocity of the center of mass. And the other way we can look at this is we know that it's going to speed up as it goes down the hill. And right now they're moving as one object. So since the velocity that it has here at the top of the hill is less than what it has here, clearly the velocity of the center of mass of the system changed. It's easy to see when they're moving as one because then we just have to worry about the velocity of that one object. Alright, so we have a situation here where Tarzan, up at some height here, swings down and scoops up Jane. The two undergo an inelastic collision, swing back up to some height, and then on the way back down, Tarzan drops Jane at the bottom of the swing, and he swings back up to some new height, which we're calling h3. And so the first question is the height here at point C greater than, less than, or equal to the height here, which was our original height? And the answer is going to be less than. So there's two reasons why we have to end at a greater height. The first is, if we think about energy, we start with gravitational potential energy, so mgh, and we're going to transition here to other gravitational potential energy when we finally swing back up here at C. However, we're now going to have more mass because we're going to have the mass of Jane added on to the mass of Tarzan. So since our total mass went up, that means our height has to go down. On top of that, there's work being done in that collision when Tarzan and Jane collide. It is an inelastic collision, so we're losing energy. So even if we didn't lose energy, we would still swing to a lower height because the mass increased. But on top of that, some work's being done in that inelastic collision. So that means we're definitely swinging to a lower height at point C. So h2 is going to be less than our initial height, h. For part B, we want to know about this h3 here, that final height of Tarzan after he drops Jane, and how that compares both to the initial height and to h2. And so the comparison is going to be less than h, the initial height, but equal to h2. So to answer this, let's think about the energy of Tarzan here. So Tarzan starts with gravitational potential energy. As he swings down, that energy becomes kinetic, and then it's back up to gravitational potential energy. Here's the important thing. Tarzan drops Jane, okay, at the bottom of his swing. When you drop someone, you're not actually exerting a force on them. So that means that at the bottom of the swing here, there is no work being done. So the gravitational potential energy that Tarzan starts with becomes the kinetic that he has at the bottom, and then is transferred back into gravitational potential. There's no change in energy. There's no gaining of mass like we had in the last one where there was the collision. There's no energy lost due to work. And so that means that he will swing back up to the same height, because the energy he started with over here is the energy that Tarzan by himself ends with. Okay? Now Jane, when she's dropped, is going to have some amount of energy, some amount of kinetic. But because there was no work being done, there was no force between the two of them, there's no transfer of energy. Tarzan doesn't gain energy from Jane, nor does he lose energy when he dropped Jane. Tarzan's energy just remains the same. And so he swings back up to the same height that he had here, which is equal to h2, and we know that already that h2 is less than h. So that's why it's less than h but equal to h2.